Something appeared on the sun in early December. Something so massive, so perfectly positioned, that scientists worldwide held their breath. I'm not talking about a normal solar flare or a routine burst of radiation. I'm talking about one of the largest sunspots of the entire year, 10 times the size of Earth, and it locked directly onto our planet like a cosmic crosshair. And here's what makes this truly unprecedented. It was comparable in size to the sunspot that caused the most devastating solar storm in recorded human history. Let that sink in for a moment. While you were shopping for holiday gifts, planning family dinners, or scrolling through your phone, a monster was staring at us from 93 million miles away. A region of the sun so magnetically twisted, so energetically charged, that it fell into the most dangerous classification scientists have, and it pointed straight at Earth during the exact window when it could do maximum damage. Stay with me for the next several minutes, because we're going to explore what happened when one of the largest sunspots of the year aimed itself at our planet, why scientists were genuinely concerned, what this means for our technology-dependent civilization, and most importantly, what actually occurred when this cosmic threat reached its peak. This isn't science fiction. This isn't exaggeration. This is what happened in our skies just weeks ago, and most people have no idea how close we came to a very different kind of December. You see, we live in a time when we've become completely dependent on technology that's shockingly vulnerable to the sun's fury. Your phone, your GPS, your bank account, the power grid keeping your home warm, the satellites guiding planes through the sky, all of it hangs by a thread when the sun decides to unleash its energy toward Earth. And in early December, that thread was tested by a sunspot complex so large, so angry-looking, that solar physicists around the world started running calculations about worst-case scenarios. But here's what makes this story different from the typical space weather news you might ignore. This wasn't just big, it wasn't just aimed at us, it was both, at the same time, during a period when the sun is at its most active in over a decade. We're living through what's called solar maximum, the peak of the sun's 11-year cycle, and this sunspot was the crown jewel of that maximum. One of the largest active regions to cross the Earth-facing hemisphere in all of the year. Think about that. Out of every sunspot that appeared in 365 days, this was the king, and it had us in its sights. Now, I know what some of you might be thinking. The sun always has sunspots. Scientists are always monitoring something. Why should this one matter? And that's a fair question. But when you understand what this particular sunspot was capable of, when you learn about its magnetic configuration and its size relative to the event that shut down telegraph systems worldwide in 1859, when you realize that our modern world is infinitely more vulnerable than the world of the mid-1800s, suddenly this stops being abstract space news and becomes something that could have affected your life in profound ways. The scientists who study our sun have classification systems for sunspots, ways of measuring their magnetic complexity and their potential for violence. Most sunspots are relatively simple, magnetically speaking. They appear, they rotate across the sun's face, they fade away without incident. But occasionally a sunspot develops what's called a beta-gamma-delta magnetic configuration. That's the most dangerous type. That's the configuration that produces the most powerful solar flares and the most devastating coronal mass ejections. And this December monster, it had exactly that configuration. Imagine standing on a field and watching storm clouds gather overhead. Now imagine those aren't just any storm clouds, but supercell thunderstorms with all the ingredients for a catastrophic tornado. That's what solar physicists saw when they analysed this sunspot complex. All the pieces were there. The size, the magnetic twist, the position, the timing, everything aligned for a potential disaster that could have made headlines around the world, not because of political drama or economic news, but because the sun decided to remind us who's really in charge of this solar system. And here's the thing that kept experts awake at night. This sunspot didn't just appear suddenly and disappear quickly. It persisted, it grew, it evolved into an even more complex structure as it rotated into the perfect position facing Earth. There was time to watch it develop, time to run models, time to realize what might be coming. And that made it worse in some ways, because knowledge without power to prevent something is its own special kind of torture. You can see the threat, you can calculate the odds, but you can't do anything except watch and hope. The historical parallel here is impossible to ignore. In September of 1859, an astronomer named Richard Carrington was observing the sun when he witnessed something extraordinary. A massive solar flare erupted from a sunspot complex, and within hours, Earth's magnetic field was in chaos. Telegraph wires sparked and caught fire. Auroras appeared as far south as the Caribbean. It was the largest geomagnetic storm in recorded history, and it happened in an era when humanity had barely begun to use electricity. Now, fast forward to today, we have satellites in orbit worth billions of dollars, we have power grids spanning entire continents, we have GPS systems guiding everything from your car to commercial aircraft to military operations. We have internet infrastructure connecting the entire planet, and all of it, every single piece, is vulnerable to the kind of solar fury that created the Carrington Event. So, when a sunspot appears that measures roughly 90% the size of the Carrington sunspot, scientists don't shrug it off. They pay attention, they model trajectories, they alert power grid operators, they brief government agencies, because they know something most people don't. We've been lucky. Remarkably, almost impossibly lucky. Since the dawn of the space age, we haven't taken a direct hit from a Carrington-class solar storm. We've had close calls, we've had glancing blows, but we haven't experienced the full force of what the sun can unleash. And in early December, with one of the largest sunspots of the year pointing directly at us, that luck was being tested. I want you to think about your morning routine. You probably check your phone before you even get out of bed. Maybe you use GPS to navigate to work. You rely on traffic lights controlled by electrical systems. Your bank transactions happen electronically. Your food supply depends on refrigeration powered by the electrical grid. Your heat, your light, your entertainment, your communication with loved ones, all of it flows through systems that could be crippled by a severe solar storm. And this December sunspot had the potential to create exactly that kind of storm. Before we go further into what actually happened, I need you to do something for me. Hit the like button on this video because what I'm about to share with you is information that more people need to understand. We live on a planet orbiting a star, and that star is not as stable as we like to pretend. Drop a comment telling me where you're watching from, because I'm genuinely curious how many different parts of the world are represented here. All of us living under the same sun, all of us equally vulnerable when it decides to lash out. And if you want to stay informed about space weather events that could actually affect your life, subscribe to this channel, because this story is just the beginning of understanding how connected we are to forces far beyond our control. Now, let's talk about what happened when one of the largest sunspots of the year crossed into the perfect position to strike Earth, and why the outcome might surprise you in ways you're not expecting. The story of this cosmic threat actually begins not on Earth, but on Mars. In late November, while humans on our planet were preparing for the holiday season, a rover sitting on the dusty surface of the red planet was doing what it does every day, monitoring the sun, and it saw something emerging around the eastern limb of our star, something that would soon capture the attention of solar physicists worldwide. The instruments on Mars, positioned at a different angle from Earth's perspective, caught the first glimpses of what would become designated as active region Fort Wonin 4 through Fort Wonin E6, a complex of sunspots that would merge and evolve into the largest solar feature of the entire year. This is one of those moments where the infrastructure of modern solar observation really matters. We're not reliant on a single telescope anymore, not limited to observations from one vantage point. We have spacecraft scattered throughout the inner solar system, each one providing a different angle, a different perspective on our star's behaviour. The Mars rovers aren't just studying Martian geology. They're part of a network monitoring the sun, giving us advance warning of what's rotating into view from the far side. And what they saw in late November was concerning enough to trigger immediate alerts to solar observation teams back on Earth. Within days, as the sun's rotation carried this active region closer to the Earth-facing hemisphere, ground-based telescopes and space-based observatories confirmed what the Mars instruments had detected. This wasn't just a large sunspot. This was a complex, a cluster of interconnected active regions with tangled magnetic field lines and enormous spatial extent, the kind of structure that makes solar physicists sit up straight in their chairs and start checking their monitoring schedules to ensure 24-hour coverage. Here's what the public didn't see during those early days of December. Behind the scenes, in solar observation centres around the world, there was a quiet but intense focus on this developing situation. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center in Boulder, Colorado was tracking it. NASA's Solar Dynamics Observatory was capturing high-resolution images every few seconds. Solar physics teams at universities and research institutions were analysing the magnetic field data, looking for signs of instability, calculating energy release potentials. This is the silent alarm I'm talking about. Not panic, not public warnings, but professional attention at the highest level. You have to understand the context here. Solar physicists monitor the sun constantly. They see sunspots appear and disappear all the time. It's routine. It's expected. The sun always has some level of activity, but every so often something appears that's not routine. Something that makes even veteran solar observers pause and take notice. And active region 424 through 426 was one of those rare events. Not because of one single characteristic, but because of the combination of factors. Size, magnetic complexity, timing within the solar cycle, and position all converged to create a situation worth genuine attention. The technical designation tells you something important. When solar physicists number active regions, they're tracking them across the sun's surface as it rotates. The numbering system helps identify and follow specific sunspot groups as they evolve and move. This particular complex received multiple numbers because it was actually several active regions that developed in close proximity, their magnetic fields interacting and creating even more complex structures. In simpler terms, this wasn't just one sunspot. It was a family of sunspots clustered together, magnetically connected, and collectively forming one of the largest active regions observed in years. As early December progressed, the sunspot complex rotated steadily toward the central meridian, that imaginary line down the middle of the sun's disk as we see it from Earth. And here's why that matters so much. When a sunspot is off to the side near the limb of the sun, any eruptions it produces tend to send material off at an angle away from Earth. We might catch the edge of the blast, but we're not in the direct line of fire. But when a sunspot crosses the central meridian, when it's dead center from our perspective, any eruption it produces is aimed straight at us like a shotgun pointed directly at the target. The geometry of the situation matters enormously, and this monster was heading right for that center position. Solar observation teams knew exactly when this crossing would occur. They could calculate it with precision. The sun rotates roughly once every 27 days as seen from Earth, so tracking the movement of surface features is straightforward mathematics. The peak danger window for active region 424 through 426 would be December 4th through 6th, when the complex would be optimally positioned to send any eruptions directly toward our planet. Mark those dates in your mind. That was the window when, if something was going to happen, it would have maximum impact on Earth. During those early December days, there was a strange duality to the situation. If you were a regular person going about your daily life, you had no idea this was happening. You weren't thinking about the sun except maybe to complain about short winter days or dark mornings. You certainly weren't aware that a sunspot complex 10 times larger than the entire planet was rotating into position to potentially unleash electromagnetic chaos on our technological infrastructure. But if you were part of the solar physics community, if you were responsible for monitoring space weather threats, if you worked for a power grid operator or a satellite company or a government agency concerned with infrastructure protection, you were paying very close attention. This is what I mean by a silent alarm. There were no news helicopters circling the sun. There were no emergency broadcasts telling people to prepare. There were no runs on stores for supplies. The general public was blissfully unaware. But the people whose job it is to understand and prepare for solar threats were absolutely aware, and they were monitoring the situation with the kind of focus you reserve for potentially serious events. Think about how different this is from other natural disasters. When a hurricane forms in the Atlantic, we track it constantly. The news covers it. People in the projected path prepare. When earthquake scientists detect unusual seismic activity, there's public awareness. But solar threats are invisible to the naked eye, at least, until they arrive and start causing problems. You can't see a coronal mass ejection heading toward Earth. You can't feel it until your GPS stops working, or your power flickers off, or your satellite TV signal disappears. The threat is real, but it's not visceral in the way that wind and water and shaking ground are visceral. So throughout early December, while holiday music played and people decorated trees and the world prepared for year-end celebrations, scientists watched the sun. They watched this massive sunspot complex rotate into position. They analysed its magnetic structure daily, looking for changes that might indicate an impending eruption. They ran models predicting what would happen if it produced a major flare and coronal mass ejection. They briefed stakeholders who needed to know, and they waited to see what would happen when one of the largest sunspots of the year reached the perfect position to strike. There's something almost surreal about that kind of waiting. You can see the threat developing, you can measure it, you can calculate probabilities, but you can't stop it. You can't push the sunspot aside or calm its magnetic fields or prevent an eruption if one is going to occur. All you can do is watch and prepare for consequences. It's like standing on a beach, watching a tsunami approach in slow motion, except instead of water, you're watching magnetic field lines twist and energy build in plasma that's hotter than anything humans can create. And all of it happening 93 million miles away, yet close enough to reach out and touch us with devastating effect if conditions align. The data coming in from observation satellites was telling a clear story. This sunspot complex was not only large but magnetically complicated in precisely the way that produces dangerous eruptions. And as it rotated closer to the optimal position for Earth impact, the tension in solar observation centers grew. Not panic, mind you. These are scientists and professionals who deal with solar activity for a living. But there was certainly heightened attention, increased monitoring, and a very clear understanding that the next few days would reveal whether this monster would live up to its threatening appearance, or whether it would pass quietly across the sun's face without incident. The stage was set, the actors were in position, and Earth was waiting in the audience, mostly unaware that the show was about to begin. Before we dive deeper into what this December threat actually did, you need to understand what you're looking at when you see a sunspot, because the word sunspot sounds almost benign, doesn't it? Like a blemish or a freckle on the sun's surface, something cosmetic, something that doesn't really matter. But that linguistic simplicity hides an almost incomprehensible reality. A sunspot is a window into forces so powerful, so energetic, that they make everything humans have ever built look like children's toys. Let me paint you a picture of what's actually happening in a sunspot. The sun is a ball of plasma, ionized gas held together by gravity, with nuclear fusion in its core pumping out energy equivalent to billions of nuclear bombs detonating every single second. That energy works its way outward through layers of the sun until it reaches the surface, what we call the photosphere. Normally, that surface has a relatively even temperature around 10,000 degrees Fahrenheit, hot enough to vaporize any material humans have ever created. But sunspots are cooler regions, around 7,000 degrees, which makes them appear darker against the surrounding brilliance. Why are they cooler? Because of magnetic fields. The sun has a powerful magnetic field generated by the movement of plasma in its interior, and sometimes those magnetic field lines bunch together, becoming so concentrated that they inhibit the normal convection of heat from below. Think of it like pinching a garden hose. The flow of water slows down at the pinch point. Similarly, the flow of heat slows down where magnetic fields are strongest, creating these cooler, darker regions we see as sunspots. But here's the critical part. Cooler doesn't mean calm. Those magnetic field lines are storing enormous amounts of energy, like springs being compressed tighter and tighter. And when they suddenly snap or reconnect, all that energy releases at once in the form of solar flares and coronal mass ejections. Now, let's talk about size, because this is where things get truly mind-bending. Earth has a diameter of about 8,000 miles. It's a substantial planet, big enough to hold all the oceans and continents and mountains and everything humans have ever known. The sunspot complex that appeared in December was roughly 10 times that diameter. Wrap your mind around that for a second. If Earth was sitting on the sun's surface, this sunspot could have swallowed 10 Earths lined up side by side. The sheer scale is difficult to process because we don't have everyday reference points for objects that large. Imagine you're standing in a field looking at a barn that's 100 feet long. Now imagine something 10 times that size, a 1,000-foot-long structure. That's big, but you can still conceptualize it. Now imagine that instead of feet, we're talking about planets. Instead of a barn, we're talking about Earth itself. And instead of 10 times a 100-foot barn, we're talking about 10 times an 8,000-mile planet. The scale becomes abstract, almost meaningless, because it's so far outside human experience. But that's what solar physicists were looking at through their telescopes. A feature on the sun large enough to swallow our entire world 10 times over. Size alone doesn't tell the whole story, though. What really matters is magnetic configuration. Remember when I mentioned beta-gamma-delta classification earlier? This is where we need to understand what that means. Solar physicists classify sunspots based on how their magnetic fields are arranged. A simple sunspot might have a clear north pole and south pole like a bar magnet, with relatively straightforward field lines. That's called a beta configuration, and it's not particularly dangerous. But as sunspots become more complex, as multiple magnetic regions interact and field lines tangle and twist around each other, the classification changes. A beta-gamma configuration means you have positive and negative magnetic polarities so close together and so mixed that they're creating irregular fields. It's like having multiple magnets jumbled together with their poles facing random directions. The field lines can't settle into a simple pattern. They're stressed, twisted, unstable. And a beta-gamma delta configuration is even worse. That designation means the magnetic fields are so tangled that you have delta structures, regions where magnetic polarity is completely inverted from what it should be, creating intense magnetic pressure. Think of it like twisting a rubber band tighter and tighter. Eventually it's going to snap back violently. That's what happens in beta-gamma delta sunspots. The magnetic fields twist until they can't twist anymore, and then they explosively reconnect, releasing energy equivalent to millions of nuclear weapons in a fraction of a second. Active region 424 through 426 had this exact configuration. Not only was it massive in size, but its magnetic structure was as complicated and unstable as sunspots get. It was the perfect storm of characteristics. Large spatial extent means more magnetic energy can be stored. Complex configuration means that energy is more likely to release violently. And when you combine both traits in a single sunspot complex aimed directly at Earth, you have a recipe for the kind of solar storm that makes it into history books. I want you to understand something about magnetic field energy. We use magnets in everyday life: refrigerator magnets, compass needles, magnetic phone mounts. These are weak, tiny magnetic fields that we can easily overcome with our hand strength. But the magnetic fields in a sunspot are millions of times stronger. They're powerful enough to channel and control plasma that's hotter than the surface of the sun, plasma moving at hundreds of miles per second, plasma with enough mass to fill volumes larger than planets. When those fields snap and reconnect, they can hurl billions of tons of that plasma into space at speeds exceeding 1,000,000 miles per hour. That's what a coronal mass ejection is. It's a magnetic explosion that throws star stuff out into the solar system, and if Earth happens to be in the path, that star stuff slams into our magnetic field and causes all the problems we're going to discuss. The December sunspot complex had all of this potential bottled up inside it. Every observation confirmed it. Every analysis of the magnetic field data showed the characteristic signs of a highly dangerous active region. The only question was whether it would actually erupt while it was facing Earth, and if it did, how powerful that eruption would be. This is the monster that solar physicists were tracking. Not a monster in the fantasy sense, but a natural phenomenon with the power to reach across 93 million miles of space and disrupt human civilization. A reminder that we live in a dynamic solar system where the star at the center can still affect us profoundly despite the vast distance. And here's what makes this December event particularly noteworthy in a historical context. This sunspot complex was measured and compared to previous major active regions. Solar physicists keep records going back decades, catalogues of significant sunspots and their characteristics. When they ran the numbers on active region 424 through 426, they found something striking. It was one of the largest sunspot complexes of the entire year in the prime of solar maximum. Out of all the active regions that had appeared on the Sun throughout the preceding months, this one took the crown. And more than that, when they compared its size to the infamous sunspot that produced the Carrington Event back in 1859, they found it was comparable in scale. It wasn't quite as large as that historical monster, but it was in the same ballpark. It was playing in the same league. That comparison is what elevated this from interesting solar activity to genuinely concerning space weather threat. Because we know what a Carrington-class event could do to modern civilization. Studies have been done, models have been run, the economic damage alone would be measured in trillions of dollars. The disruption to daily life would be catastrophic in ways that are hard for most people to imagine. And here was a sunspot approaching that same size, with that same dangerous magnetic configuration, aimed directly at us during a solar maximum when the sun is most active. All the ingredients were present, all the pieces were in place. The only unknown was whether the recipe would actually cook into disaster, or whether we'd get lucky one more time. Understanding what this monster was made the waiting that much more intense. To truly understand why scientists were so focused on this December sunspot, we need to go back in time, not just months or years, but more than a century and a half, to September 1st and 2nd, 1859. This is where the ghost that haunts every solar physicist comes from, the historical event that serves as the benchmark for worst-case scenarios. It's called the Carrington Event, named after the British astronomer Richard Carrington, who witnessed the solar flare that triggered it. Imagine you're living in the Victorian era. The Industrial Revolution is transforming society. Telegraph wires are strung across continents, creating the first global communication network in human history. It's cutting-edge technology, the internet of its time, allowing messages to travel instantly across thousands of miles where previously information moved only as fast as horses or ships could carry it. On the morning of September 1st, 1859, Carrington was doing what he did most clear days, observing the sun through his telescope, carefully drawing the sunspots he saw onto paper. This was how solar observation worked back then. No cameras, no satellites, just patient hand-drawn records of what the sun looked like day after day. And then, as he watched, something extraordinary happened. He saw a bright flash erupt from a sunspot group, a sudden brilliant white light that lasted about 5 minutes. He had just witnessed, without knowing exactly what he was seeing, a massive solar flare, the largest solar flare in recorded history. The energy from that event raced across space at the speed of light, reaching Earth in about 8 minutes, but the flare itself was just the opening act. The real danger was what followed. A coronal mass ejection, billions of tons of plasma and magnetic field hurled out from the sun's corona, travelling much slower than light, but carrying far more physical impact. That CME reached Earth roughly 18 hours later, which tells you something about how fast it was moving. Most coronal mass ejections take 2 to 3 days to reach Earth. This one made the journey in less than a day, which means it was travelling at exceptional speed, carrying exceptional energy. When it slammed into Earth's magnetic field, the results were spectacular and terrifying in equal measure. The aurora borealis, normally confined to high latitudes near the Arctic, appeared as far south as the Caribbean. People in Hawaii saw it. People in Central America saw it. The sky lit up with shimmering curtains of green and red light that had never been seen at those latitudes before and haven't been seen since. But the aurora was just the visible symptom of what was happening. Earth's magnetic field was being compressed and distorted by the CME's magnetic field. Currents were being induced in anything conductive on the surface, and in 1859 that meant telegraph wires. Telegraph operators reported sparks jumping from their equipment. Some received electrical shocks. Papers caught fire from the induced currents. In some locations, telegraph systems continued to work even after their batteries were disconnected, powered entirely by the currents induced by the geomagnetic storm. It was a global disruption of the most advanced technology of the time. Now here's the critical question. What would the Carrington event do to our world today? And the answer should frighten you, because we are infinitely more dependent on electricity and electronics than the Victorians were on telegraphs. Let me walk you through what a Carrington-class solar storm would mean for modern civilization. Start with the power grid. The electrical infrastructure that powers everything in modern life operates on a delicate balance. Power plants generate electricity, transmission lines carry it across distances, transformers step the voltage up and down as needed, and distribution systems deliver it to your home. It's an interconnected web spanning entire continents. When a geomagnetic storm strikes, it induces currents in those long-distance transmission lines, currents that can overload transformers. And large transformers, the kind that form the backbone of the power grid, are not mass-produced items sitting in warehouses ready for replacement. They're custom-built pieces of equipment that can take months or even years to manufacture and install. If a Carrington-class storm took out hundreds of transformers across North America or Europe, the grid wouldn't just go down for hours or days. We could be looking at months or years before full power restoration in some regions. Think about what that means. No power for weeks or months. Your refrigerator stops working. Your food spoils. Grocery stores can't keep products cold. The supply chain that depends on refrigerated transport breaks down. Gas stations can't pump fuel without electricity. Even if you have a generator, how long will your fuel supply last? Water treatment plants go offline, meaning no clean water coming from your taps. Sewage systems fail, hospitals lose power, and backup generators are only good for days if they can't refuel. This isn't just inconvenience. This is the potential collapse of the infrastructure that keeps millions of people alive in modern cities. But it gets worse. Satellites. We have thousands of satellites in orbit, handling everything from GPS to communications to weather monitoring to military reconnaissance. During a severe geomagnetic storm, satellites are exposed to intense radiation and can experience electrical damage or complete failure. GPS satellites are particularly vulnerable, and we depend on GPS for far more than just finding directions on your phone. Aviation uses it for navigation, shipping uses it for routing, the financial system uses it for timestamping transactions. Precision agriculture uses it for planting and harvesting. Military operations depend on it absolutely. If GPS goes down globally for an extended period, the cascade effects would ripple through every sector of the economy. Then there's the internet, the global communication network that has become as essential as electricity itself. Undersea cables, satellite links, fiber optic networks, data centers, all of it depends on electrical power and functioning electronics. A Carrington-class storm could damage infrastructure at multiple points simultaneously. We could see regional internet outages lasting days or weeks. And in a world where business, education, government, and personal communication all flow through the internet, that kind of disruption would be catastrophic. I want you to think about your personal life for a moment. Imagine waking up tomorrow to no power, no internet, no cell phone service, no GPS, no functioning ATMs or credit card systems. Your bank account still exists somewhere in a database, but you can't access it. You can't prove how much money you have. Cash becomes the only currency, and how much cash do you have on hand? How long would it last? How would you buy food, water, medicine? How would you communicate with family members across the country? How would society function when all the systems we take completely for granted suddenly stop working? This is why the comparison between the December sunspot and the Carrington sunspot matters so much. The Carrington event happened in a world that was barely electrified. We lost telegraphs for a while. It was disruptive but not civilization-threatening. The same event today, a Carrington-class solar storm hitting our modern technological infrastructure, would be a global emergency on a scale that would make most natural disasters look minor by comparison. Hurricanes affect regions, earthquakes affect regions. Even pandemics, as we've learned, can be managed with modern medicine and coordination. But a severe solar storm affects the entire daylit side of the planet simultaneously, and it takes out infrastructure that we have no rapid replacement plan for. Studies have estimated the economic cost of a severe solar storm at multiple $1 trillion, and that's probably conservative. But the economic cost is almost beside the point. The real question is how society functions when the technological systems that enable modern life all fail at once. How do supply chains work? How do hospitals operate? How do we distribute food and water? How do we maintain order when communication systems are down and people are frightened? These aren't abstract questions. They're real contingencies that emergency planners think about and hope they never have to implement. So when solar physicists saw a sunspot complex in December that was comparable in size to the Carrington sunspot, with an even more dangerous magnetic configuration aimed directly at Earth during solar maximum, you can understand why there was genuine concern. Not panic, because these are rational scientists who deal in probabilities and data, but concern because they know what's at stake. They know that we've been lucky so far. They know that eventually our luck will run out. The sun will produce another Carrington-class storm. It's not a question of if, but when. And every time a massive, magnetically complex sunspot aims at Earth, there's a chance that when is now. The ghost of September 1859 hangs over every major solar threat. It's the benchmark, the historical precedent, the proof that the sun can and has unleashed this kind of fury on Earth. And it happened during a solar cycle that was actually less active than the one we're experiencing now. The Carrington event wasn't even the largest solar storm the sun is capable of producing. Ice core records suggest there have been even larger events in the distant past, before humans had technology vulnerable to space weather. But Carrington is the one we have detailed historical records for, the one we know affected technology, the one we can study and model and extrapolate from. And when a sunspot appears that rivals the Carrington sunspot in size and exceeds it in magnetic complexity, that ghost becomes very real, very present, very relevant to the decisions and preparations happening behind the scenes. This December, that ghost was staring at us from the sun's surface. The question was whether it would reach out and touch us the way it did in 1859, or whether it would pass quietly by, leaving us to breathe a sigh of relief and continue our technological lives for a little while longer. The historical parallel made this more than just another space weather event. It made it a test of our luck, a roll of the cosmic dice, a moment when past and present aligned in a way that could have written a very different kind of history. Numbers in science are supposed to be cold. objective, emotionless. They're just measurements, data points, values on a chart. But sometimes a number carries weight beyond its mathematical meaning. Sometimes a number tells a story that words struggle to capture. And the comparison to Carrington scale dimensions, in the context of this December sunspot, is what makes solar physicists pause and reconsider the reassurances they might have been planning to give. When scientists measured active region 424 through 429X, when they calculated its spatial extent and compared it to historical records, they found it was comparable in size to the sunspot complex that caused the Carrington event, approaching similar dimensions. Not 50%, not 30%, comparable scale. That's not just big. That's in the same class, the same category, the same league as the historical benchmark for worst-case solar storms. It's close enough that the difference starts to feel academic rather than practical. Think about it this way. If someone told you a hurricane was bearing down on your city and it was 90% as powerful as the strongest hurricane ever recorded, would you feel safe? Would you think, well, it's only 90%, so I'm fine? Or would you start preparing for the worst? A Carrington-scale sunspot is catastrophic potential. A sunspot approaching those dimensions is devastating potential. And a solar storm comparable to the one that shut down the most advanced technology of its era, in a world far less dependent on that technology than we are today, is absolutely something to take seriously. But size is only part of the equation. Remember the magnetic classification we discussed. Beta gamma delta, the most dangerous configuration, the type that stores the most energy and releases it most violently. The Carrington sunspot had a complex magnetic field, no question. But modern observation techniques allow us to map magnetic fields with far greater precision than was possible in the 1800s. And when solar physicists analysed the December sunspot complex, they found it was not only comparable in size to Carrington, but potentially even more magnetically twisted and unstable. This is where the danger calculation escalates. Imagine two cars both speeding down a highway. One is going 80 miles per hour, the other is going 90. Both are dangerous. Both can cause catastrophic accidents. But the one going 90 has more kinetic energy, will hit harder, will cause more damage. Now imagine those cars are carrying explosives. The faster one doesn't just hit harder, it detonates with more force. That's the analogy for magnetic energy in sunspots. A larger, more complex magnetic field doesn't just mean a bigger eruption. It means an exponentially more powerful release of energy, potentially driving a coronal mass ejection faster and with more mass than a smaller, simpler sunspot could manage. So we had a sunspot complex that was comparable in size to Carrington, with equal or greater magnetic complexity aimed directly at Earth. And there's another factor that made this particularly significant: timing. The Carrington event happened in September, near the peak of a solar cycle that was moderately active by historical standards. Our current solar cycle, cycle 25, has been more active than predicted. We reached solar maximum earlier than expected and with more sunspots than the forecast suggested. The sun is, for lack of a better term, overperforming. And in the middle of that overperformance, during the peak activity period, this monster appeared. The specific danger window was clear from orbital mechanics. As the sunspot complex rotated across the sun's face, scientists knew exactly when it would cross the central meridian, that point where it would be directly facing Earth. December 4th through 6th. Mark those dates. For approximately 72 hours, if this sunspot decided to erupt with a major flare and CME, Earth would be in the direct line of fire, not a glancing blow, not catching the edge of the blast. Full frontal impact with minimal warning time. Here's what makes that timing particularly nerve-wracking. A coronal mass ejection takes time to reach Earth, usually 1 to 3 days depending on its speed. But a CME from a sunspot at the central meridian, especially a fast-moving one driven by a powerful flare, could reach Earth in as little as 15 to 18 hours. That's not much time to prepare. That's barely enough time to alert power grid operators, airline systems, satellite companies, and government agencies. It's certainly not enough time to do anything structural to protect infrastructure. You're basically watching the bullet travel through the air toward you, knowing impact is coming, unable to move out of the way. The Beta Gamma Delta classification meant this sunspot had all the ingredients for a major eruption. Think of it like watching storm, conditions before a tornado. Meteorologists can see when atmospheric conditions are ripe for tornado formation. They can see the rotation in the clouds, the temperature gradients, the wind shear. They can say with confidence that the ingredients are present, but they can't predict exactly when or where a tornado will touch down until it actually happens. Solar flares are similar. Scientists can see when conditions are ideal, when magnetic energy is stored and ready to release. But they can't predict the exact moment of eruption or its precise magnitude until it occurs. Throughout December 4th, 5th and 6th, this uncertainty hung over the solar physics community. Every observation update was checked carefully. Every change in the sunspot's magnetic structure was analysed for signs of impending eruption. The sunspot was being watched more closely than any active region had been watched all year, simply because of its size, position, complexity and timing. All the factors aligned to make this a genuine threat window. And here's what adds another layer to the tension. Sunspots often produce their most powerful eruptions when they're near the central meridian. There's something about the magnetic stress at that point in the rotation, something about the geometry of the fields that seems to trigger major releases of energy. It's as if the sunspot knows it has a clear shot and decides to take it. So not only was this December monster in the perfect position to hit Earth, it was also in the position where it was statistically most likely to actually erupt. Carrington comparable size, beta-gamma delta configuration, central meridian position, solar maximum timing. Every factor that could make a sunspot dangerous was present simultaneously. This wasn't just one warning flag, it was all the warning flags at once. And that's why, despite the public being largely unaware, despite no emergency broadcasts or dramatic news coverage, the people who understand solar threats were paying very, very close attention during those December days. The probability of a major eruption from any given sunspot, even a dangerous one, is not 100%. Most sunspots, even complex ones, produce some flaring activity but don't create the kind of catastrophic CME that threatens civilization. The odds were still in Earth's favour, statistically speaking. But when you're talking about a scenario that could cause trillion-dollar damage and disrupt billions of lives, even a small probability becomes significant. If there's a 10% chance of catastrophic impact, do you ignore it? If there's a 5% chance, do you dismiss it? Where's the line between acceptable risk and necessary concern? Solar physicists don't have the luxury of dismissing possibilities just because they're unlikely. They have to consider worst-case scenarios because the consequences of being wrong are so severe. So when they calculated the potential of this December sunspot, when they ran their models and checked their data and confirmed that yes, this was 90% of Carrington with possibly worse magnetic complexity, they couldn't just shrug it off. They had to treat it as the serious threat it was, monitor it continuously, and prepare for the possibility that Earth's luck might be running out. The Carrington comparison became shorthand for all of this complexity, all of this concern, all of this potential danger compressed into a single comparative figure. It wasn't just a measurement, it was a warning, a reminder, a historical echo reaching across more than a century and a half to tell us that what happened before can happen again, and when it does, we need to be ready. And in December, for 72 critical hours, that warning was active, that threat was real, and the world waited, mostly unknowing, to see what the largest sunspot of the year would actually do when it had Earth perfectly in its sights. And then something unexpected happened. Or more precisely, something unexpected didn't happen. As active region Fort Woonin 4 through Fort Woonin Essex rotated through the danger window, as it crossed the central meridian during December 4th through 6th with Earth directly in its line of fire, as solar physicists watched and monitoring systems tracked every fluctuation in its magnetic field, the sunspot complex exhibited behaviour that was both relieving and deeply puzzling. It remained relatively quiet. This requires some explanation, because quiet is a relative term when you're talking about a feature 10 times the size of Earth, with enough magnetic energy to power human civilization for millions of years. The sunspot wasn't completely inactive, it was producing elevated thermal emissions, its magnetic fields were definitely churning and evolving, there was activity happening. But what it wasn't doing, what everyone had been watching for, was erupting with a major X-class flare and a massive coronal mass ejection. It wasn't unleashing the fury that its size and configuration suggested it was capable of. Put yourself in the position of a solar physicist during those December days. You're looking at all the data, you see the size, you see the magnetic complexity, you see the perfect Earth-pointing position. Every indicator suggests this sunspot should be violently active. Historical patterns tell you that sunspots like this tend to produce significant eruptions. The magnetic energy is there, stored in those twisted field lines ready to release. And yet, hour after hour, day after day, the major eruption doesn't come. The beast is growling but not attacking. The loaded gun is pointed but not firing. This kind of situation is almost more stressful than immediate action would be, in some ways. When something expected happens, you can respond. When a sunspot erupts, you track the CME, you calculate arrival time, you alert the appropriate systems, you take protective measures. There's a clear sequence of events and responses. But when a dangerous sunspot sits there, doing nothing major, you're left in a state of suspended tension. Do you relax? Do you assume the danger has passed? Or do you maintain vigilance because the threat hasn't actually gone away, it's just been delayed? Solar physics gives us some understanding of why sunspots behave the way they do, but it's not a perfect science. We can't predict with certainty when a sunspot will erupt any more than seismologists can predict exactly when an earthquake will strike a fault line. We know the energy is building. We know the conditions are present. But the trigger, the final factor that causes the magnetic fields to snap and reconnect, remains partially mysterious. It might be an additional twisting of the field lines. It might be an interaction with nearby active regions. It might be something we don't yet fully understand about plasma dynamics at solar temperatures and pressures. So throughout the peak danger window, active region Fortwonin 4 through Fortwonin 6 sat on the sun's surface like a coiled spring that never released. It maintained its size. It maintained its complex magnetic configuration. It rotated through the perfect Earth-pointing position. And it didn't produce the catastrophic eruption that its characteristics suggested was possible. This strange silence was, in one sense, exactly what everyone hoped for. No eruption means no threat, no damage, no disruption. Earth gets to continue its technological existence undisturbed. But in another sense, the silence raised questions that scientists are still contemplating. Was the sunspot complex dissipating its energy gradually through smaller-scale processes that don't produce major CMEs? Magnetic fields can release energy in multiple ways. Sometimes it happens explosively, all at once, creating those massive flares and CMEs we worry about. But sometimes energy can leak away more slowly through smaller reconnection events, through the gradual shifting of field lines, through processes that don't create singular dramatic eruptions. If the December sunspot was releasing its stored energy through these gentler mechanisms, that would explain why it didn't erupt violently despite having the capacity to do so. Or was the energy still building, still accumulating, waiting for some unknown trigger that just never materialized during the Earth-facing window? This is the scenario that keeps solar physicists up at night. Imagine a bomb that's armed and ready but hasn't been detonated yet. The potential for explosion exists. The explosive material is there. The detonator is in place. It just hasn't gone off. That doesn't mean it's safe. It means the trigger hasn't been activated. And if the trigger never comes, if the bomb is eventually disarmed through other means, everyone breathes easier. But during the time when it could go off at any moment, the tension is almost unbearable. There's also a third possibility that's worth considering. Maybe the sunspot complex simply wasn't as unstable as the measurements suggested. Magnetic field observations from Earth and near-Earth orbit give us incredibly detailed information about sunspot structure, but they're still observations from 93 million miles away. It's possible that the three-dimensional structure of the magnetic fields, in ways we couldn't fully resolve, was actually more stable than the two-dimensional projection suggested. Maybe the field lines, despite being twisted and complex, were configured in a way that resisted the kind of catastrophic reconnection that produces major eruptions. Solar physics is a science built on observation, modelling, and probability. We can't put instruments directly into a sunspot to measure conditions from the inside. We can't run controlled experiments on the sun. We observe from a distance, we build mathematical models of what we think is happening, and we compare those models to observed behaviour to refine our understanding. But there are always unknowns, always factors we might not be accounting for, always surprises when nature decides not to follow the script we've written based on past experience. The strange silence of the December sunspot became its own kind of mystery. A negative event, a non-occurrence, that was just as scientifically interesting as an eruption would have been. Why didn't it erupt? What factors prevented or delayed the release of all that magnetic energy? Was it luck? Was it physics we don't fully understand? Was it simply that the conditions, despite appearing ripe for eruption, were missing some critical ingredient that we can't yet measure or model accurately? For the people monitoring the situation, the silence was a gift. No news is good news when you're watching for potentially civilization-disrupting solar storms. Every hour that passed without a major eruption was an hour closer to the sunspot rotating past the danger zone, reducing the threat. By December 7th and 8th, as the active region moved beyond the central meridian and started heading toward the western limb of the Sun, the direct threat to Earth decreased significantly. Even if it erupted at that point, the CME would be angled away from us, likely to miss entirely or deliver only a glancing blow. But the silence also meant there was no resolution, no answer to the question of what this sunspot was truly capable of. Did we dodge a bullet, or was there never really a bullet to dodge? Did Earth get lucky, or were the threat assessments overstated? These aren't questions with easy answers. Solar physics deals in probabilities and possibilities, not certainties. All anyone could say with confidence was that the largest sunspot of the year, with all its dangerous characteristics, had passed through the peak danger window without creating a major Earth-directed eruption. That was the observable fact. The interpretation of what it meant was more complex. There's a human tendency to interpret non-events as signs that the concern was overblown, that the experts were wrong to worry. But that's not how risk assessment works. If you evacuate a coastal city for an approaching hurricane and the hurricane turns away at the last minute, that doesn't mean the evacuation was wrong. It means the low probability outcome occurred and everyone got lucky. The decision to evacuate was still correct based on the information available at the time. Similarly, the attention paid to the December sunspot was justified by its characteristics, regardless of the fact that it didn't ultimately produce a major eruption. The potential was real. The risk was real. The outcome being favourable doesn't retroactively erase the threat that existed. As December progressed and the sunspot rotated farther from the Earth-facing position, the tension began to ease. Not because the sunspot had disappeared, but because geometry had saved us. The gun was still loaded, but it was no longer pointed at us. And in solar observation, sometimes that's the best outcome you can hope for. Not the elimination of the threat, just the fortunate circumstance of the threat not being aimed in your direction when it decides to manifest. The strange silence of active region 424 through 429 helix will be studied for years to come. Every major sunspot contributes data to our understanding of solar behaviour. This one will be particularly interesting precisely because it didn't behave as violently as its characteristics suggested it could. Understanding why not is just as important as understanding why other sunspots do erupt. Every piece of data, every observation, every non-event as well as event, contributes to the larger picture of how our sun works and how we can better predict its behaviour in the future. But in the immediate term, in those December days when the world went about its business unaware of what was potentially hanging over it, the silence was simply a relief, a fortunate pause in a story that could have gone very differently. Now we arrive at the resolution, the answer to the question that's been building throughout this story. What actually happened when the largest sunspot of the year aimed itself at Earth? And the answer is both reassuring and sobering, a mixture of relief that things weren't worse, and acknowledgement that there were real effects, real consequences, real reminders that the sun can reach out and touch us even when we avoid the worst-case scenario. On December 1st, as active region 424 through 416 was still approaching the optimal Earth-facing position, the sun produced a significant solar flare from another active region. Not the catastrophic X10 or X20 class eruption that would have been truly devastating, but an Zom.9 class flare, which is still classified as strong and capable of causing noticeable effects. This flare sent radiation streaming toward Earth at the speed of light. Within minutes, the effects were felt. Radio operators in Australia, which was in the daylight hemisphere facing the sun at the time, reported sudden blackouts across multiple frequency bands. High-frequency radio communications, the kind used by aviation, maritime operations and amateur radio enthusiasts, were disrupted. The ionosphere, that layer of Earth's atmosphere where radio waves bounce to enable long-distance communication, was suddenly flooded with X-rays and extreme ultraviolet radiation from the flare. That radiation ionized the atmosphere more intensely than normal, changing its properties in ways that absorbed radio signals instead of reflecting them. This is what solar physicists call a radio blackout event, and while it's not the kind of thing that makes headlines or causes widespread public alarm, it's absolutely a real and significant impact. Imagine you're a pilot flying across the Pacific Ocean, relying on high-frequency radio to communicate with air traffic control. Suddenly your radio goes dead. You can't hear the controllers. They can't hear you. You're not in immediate danger. Modern aircraft have multiple backup communication systems and navigation tools, but it's an unsettling situation that requires crew coordination and protocol shifts to alternative communication methods. This happened to multiple flights over the Pacific and Indian Ocean regions when the December 1st flare struck. Or imagine you're a ship captain in the middle of the ocean, using radio to coordinate with other vessels and receive weather updates. When that radio suddenly stops working, you're more isolated, more dependent on your own local observations, cut off from the network of information that makes modern maritime navigation safe. Again, not immediately catastrophic, but definitely a degradation of safety margins and operational capability. These effects lasted for about an hour before the ionosphere recovered and normal radio propagation resumed. The flare was accompanied by a coronal mass ejection, but this is where Earth caught a significant break. The eruption came from active region 14274, which was near the Sun's limb, not the central meridian. The CME was directed mostly away from our planet and was not geo-effective. We didn't catch the blast at all. The geometry completely favoured us. While a CME was launched with the flare, it was directed mostly away from Earth and was not geo-effective. Any geomagnetic activity around December 3rd was likely caused by other solar wind streams, not this particular CME. Not the severe or extreme storm that a direct high-speed CME would cause, but enough to create noticeable effects. Earth's magnetic field was compressed and disturbed. Currents were induced in power lines at high latitudes, though not enough to cause transformer damage or widespread power outages. Satellite operators noticed increased drag on spacecraft in low Earth orbit as the upper atmosphere heated and expanded from the geomagnetic activity. And then there were the auroras. For people living at mid-latitudes in northern regions like southern Canada, northern United States, northern Europe, the night sky on December 3rd and 4th lit up with aurora displays. The northern lights pushed farther south than they typically do, visible to millions of people who don't usually get to see this phenomenon. From a purely aesthetic standpoint, the geomagnetic storm was a gift, a reminder of the connection between Earth and the Sun made visible in shimmering curtains of light. But here's what's important to understand. These effects, the radio blackout, the moderate geomagnetic storm, the mid-latitude auroras, these were all real consequences of solar activity from active region 4114 through 41E6. This wasn't a non-event. Earth was not untouched. The sunspot did affect us, but the scale of the effects was manageable, within the range of what our technology and infrastructure are designed to handle. It was an inconvenience, a disruption, a show, but not a disaster. Now let's talk about why it wasn't worse, because that's just as important as what actually happened. Several factors worked in Earth's favour during this event. First, the timing of the X-class flare. It occurred on December 1st from a region near the Sun's limb, not from AR 4294426, when it was optimally positioned. The CME missed Earth entirely. If AR 4294426 had produced a similar flare 3 or 4 days later, when it was directly at the central meridian, the CME trajectory would have been aimed straight at us. The difference between a miss and a direct hit is enormous in terms of impact. Second, regarding CMEs from AR 4294426 during the peak danger window, there weren't any major Earth-directed ones. The Sunspot complex remained relatively quiet during its central meridian crossing, on December 4th through 6th. This was the fortunate outcome that allowed us to avoid the worst-case scenario entirely. Third, modern solar monitoring provided crucial observations throughout the event. Satellites tracked AR 4294442 tsunami continuously as it crossed the danger window. When the X1.9 flare occurred on December 1st, alerts were immediately sent to relevant authorities. The fact that no major Earth-directed CME followed from AR 44296 during its peak position was monitored in real time. Satellites were reoriented to minimize exposure to the charged particle environment. Power grid operators were monitoring their systems for unusual currents and ready to take protective measures if needed. This kind of early warning system didn't exist in Carrington's time. The telegraph operators had no idea what was coming until it was already hitting them. We do better now. Fourth, we benefited from simple geometry. AR 4294426's position during its most dangerous characteristics meant that any eruptions would have been Earth-directed, but those eruptions simply didn't occur at the expected level. The sunspot remained relatively quiet during the critical window likely dissipating energy through smaller-scale processes rather than catastrophic eruptions. All of these factors combined to turn what could have been a major event into a manageable one. But here's the sobering part of this story. Change any one of those factors, and the outcome could have been very different. If the X-class flare had erupted 3 days later, when the sunspot was perfectly positioned, direct hit instead of glancing blow. If the CME had been faster, more energetic, more massive, severe storm instead of moderate. If Earth's magnetic field had been in a weakened state for other reasons, less protection, more impact. If the eruption had been an extend flare instead of zone 0.9, exponentially more energy, potentially overwhelming multiple safeguards. This is what risk assessment in solar physics comes down to. We dodged the worst-case scenario with the December sunspot, but it wasn't because the threat was imaginary or overstated. It was because several factors happened to align in our favour. The sunspot was real. Its dangerous characteristics were real. Its potential for creating a major Earth-directed eruption was real. What was uncertain was whether all the necessary conditions would align to make that potential into reality. And in this case, they didn't quite align. We caught a break. The Zone 0.9 flare and its associated CME were essentially warning shots, demonstrations of what the sunspot could do, but not the full fury it was capable of unleashing. It's like a predator making a mock charge, showing its teeth, getting close enough to be threatening but ultimately veering away. You still felt the fear, you still recognized the danger, but you didn't suffer the full attack. That's what December was for Earth. We felt the effects of a large, dangerous sunspot aimed at us. We experienced real disruptions, but we didn't face the full catastrophic impact that the sunspot's size and magnetic complexity suggested was possible. Solar physicists will study the December 1st flare and CME in detail, analysing the data to understand why the eruption happened when it did, why it was the magnitude it was, and why the sunspot didn't produce additional major eruptions during the peak danger window. Every event contributes to the larger database of solar behaviour, helping refine models and improve predictions. And this event, with its combination of threatening characteristics and ultimately moderate outcome, provides valuable data points about how large, complex sunspots behave. For the general public, the story of what actually happened is one of relief mixed with an educational opportunity. We didn't face disaster, which is obviously good news, but we did face real effects, real reminders that space weather is not an abstract concept for scientists to worry about. It's a practical concern that can and does affect the technology we depend on. The radio blackouts over Australia were real. The geomagnetic storm was real. The auroras were real. They were all consequences of solar activity from that massive sunspot. We just happened to avoid the worst consequences through a combination of favourable circumstances and the protective factors that space weather science and Earth's natural defences provide. As December progressed beyond the peak danger window, as the sunspot rotated past the optimal Earth-facing position, the immediate threat decreased. But the sunspot didn't disappear. It continued to exist, continued to evolve, continued to be monitored as it moved toward the western limb of the sun from Earth's perspective. And that brings us to the next question. What happened after the sunspot rotated away from facing Earth? Did it pose a continued threat? Could it come back? The sun rotates. This is such a fundamental fact of solar observation that it's easy to take for granted, but it's the mechanism that both creates and resolves solar threats from Earth's perspective. The sun completes one full rotation approximately every 27 days as seen from Earth. That means any feature on the sun's surface, including sunspots, will rotate across our field of view, spending roughly 2 weeks on the Earth-facing hemisphere and 2 weeks on the far side where we can't see it directly. For active region Fortwooning 4 through Fortwooning E6, this rotation was both the source of the threat and ultimately the factor that ended the direct danger. As the sunspot complex crossed the central meridian during the peak danger window of December 4th through 6th, without producing a major Earth-directed eruption, it continued its inexorable journey across the sun's disk. By December 7th and 8th, it was past the central meridian, moving toward the western limb. Any eruptions at that point would be angled away from Earth, likely to miss us entirely or deliver only the most glancing impact. By mid-December, the sunspot complex had rotated around to the far side of the sun from Earth's perspective. We couldn't see it directly anymore with Earth-based or near-Earth orbit instruments. It was still there, still potentially active, still a massive and magnetically complex feature. but it was no longer our immediate concern because it wasn't aimed at us. The geometry of the situation had changed in our favour. The cosmic crosshair had swiveled away. This raises an interesting question that I'm sure occurred to many people following the story. Could it come back? The Sun rotates once every 27 days, which means anything on the Sun's surface will eventually rotate back into Earth-facing view. If the December sunspot persisted, if it survived as a coherent active region instead of dissipating, could we face a second threat window roughly a month after the first? The answer is complicated because sunspots are not permanent features. They're temporary manifestations of magnetic field concentrations, and they typically last anywhere from a few days to a few months depending on their size and magnetic strength. Large sunspots tend to last longer than small ones, which would suggest that a monster like active region 4 through 4 E6 might persist through multiple rotations. But persistence doesn't mean stability. Sunspots evolve, their magnetic fields change, they can break apart into smaller regions or merge with other active areas, they can strengthen or weaken over time. As the December sunspot rotated onto the far side of the Sun, solar physicists lost direct visual observation, but they weren't flying completely blind. There are techniques for monitoring the far side of the Sun using helioseismology, which analyzes sound waves traveling through the Sun's interior, and by observing the stereo spacecraft which orbits at a different angle from Earth and can see parts of the Sun that are hidden from our direct view. These methods don't provide the same detailed, real-time information as direct observation, but they can give indications of major active regions existing on the far side. The data from these far-side observation techniques suggested that the active region did persist for at least part of its far-side transit, but it was evolving and possibly weakening. By the time the sunspot would have rotated back into Earth-facing view in early January, observations showed that the active region had significantly dissipated. It was no longer the massive, highly complex sunspot cluster that had existed in early December. It had either broken up into smaller, less threatening regions, or faded away as the magnetic fields diffused and weakened. This is actually typical behaviour for large sunspots. They don't last forever. The magnetic fields that create them are maintained by processes in the Sun's interior, and when those processes shift or the fields reach the surface and interact with the solar atmosphere, they gradually lose coherence. Think of it like a whirlpool in water. It can persist for a while, maintaining its structure, but eventually the energy that created it dissipates, and the whirlpool dissolves back into random motion. Sunspots follow similar patterns on much larger scales, and with magnetic forces instead of fluid dynamics. So the direct answer to could it come back is that the specific sunspot complex that threatened Earth in early December did not return as the same threat in January. The window closed not just because of rotation geometry, but because the sunspot itself evolved past its peak size and complexity. By the time it would have been facing Earth again, it was no longer the monster it had been. Earth's luck held in multiple ways. The sunspot didn't erupt catastrophically when it was facing us, and it didn't persist long enough to threaten us during a second rotation. But there's a broader context to consider here. While that specific sunspot complex may have dissipated, we're still living through solar maximum, the peak of solar cycle 25. The conditions that allowed such a large and complex sunspot to form in December haven't gone away. The Sun is still at its most active. New sunspots are forming regularly. Some of them are large, some are magnetically complex, and any one of them could potentially develop into another major threat. This is the important takeaway from the rotation story. The threat from one specific sunspot has passed, but the underlying solar conditions that create such threats persist. We're not returning to solar minimum, the quiet period of the cycle when sunspots are rare and usually small. We're in the active period, and will remain in elevated activity levels for at least another year or two before the Sun begins its gradual decline back toward minimum. During that time, more large sunspots will appear, more X-class flares will erupt, more coronal mass ejections will be hurled into space, and some of them will inevitably be aimed at Earth. The rotation of the Sun is both a threat and a protection. It's a threat because it brings new active regions into Earth-facing view regularly, creating a constant cycle of potential danger, but it's a protection because any given sunspot has a limited window when it can threaten us directly. If we can weather the storm, metaphorically speaking, for the 2 weeks that a dangerous sunspot is facing our direction, rotation will eventually carry it away and reduce the immediate danger. We just have to get lucky repeatedly, avoiding catastrophic eruptions during the windows when geometry makes us vulnerable. As December turned to January and the immediate threat from active region 424 through 420E6 faded into history, solar observation teams continued their work. They tracked new sunspots as they appeared. They monitored existing active regions for signs of instability. They provided space weather forecasts and alerts based on current conditions. The fact that one major threat had passed didn't mean vigilance could end. It just meant attention shifted to the next potential threat, and the next after that. For those of us who aren't solar physicists, who don't spend our days watching the sun through specialized instruments, the rotation away of the December sunspot was simply a return to normal. The threat we didn't know existed was now gone in ways we also didn't directly perceive. Life continued, technology continued to function, the power stayed on, GPS kept working, the internet remained connected, all the things we take for granted remained granted. And that's how it should be. That's what space weather monitoring is supposed to achieve. Identify threats, track them, prepare for them, and hopefully watch them pass without causing catastrophic damage. The December sunspot's rotation away closed one chapter in the story of Solar Cycle 25, but it didn't end the book. The sun's story continues every day, every rotation, every cycle. And as long as we remain a technologically dependent civilization living on a planet, orbiting an active star, that story will matter to us in very practical ways whether we pay attention or not. Let me put the December sunspot event into its proper context, because this wasn't an isolated incident or a fluke occurrence. This was one example, one data point, one episode in a much larger story about where we are in the solar cycle and what that means for the coming months and years. We are living through solar maximum, and that simple phrase carries implications most people don't fully appreciate. Solar cycle. 25 officially began in December 2019, though it took a while for solar activity to ramp up noticeably. For the first couple of years, sunspot numbers were low, and activity was minimal, exactly as expected during the climb out of solar minimum. But as 2022 and 2023 progressed, something interesting started happening. The sun became more active than predictions suggested it would. The models that forecast solar cycles based on historical patterns had predicted a relatively modest maximum, with peak sunspot numbers around 115. But the sun had other ideas. By late 2023 and into 2024, monthly sunspot counts were regularly exceeding predictions. The sun was overperforming, producing more sunspots, more active regions, more flares than the forecasts anticipated. And in October 2024, we hit what appears to be the peak of this cycle, 161 sunspots in a single month. That's significantly higher than predicted, higher than the previous cycle's maximum, and approaching the levels seen in some of the stronger cycles of the past century. What this means practically is that we've entered a period of elevated solar activity that will persist for at least another year or two. Solar maximum isn't a single moment, it's a plateau, an extended period around the peak of the cycle when sunspot numbers remain high and the probability of major solar events is elevated. We're on that plateau now. The December sunspot was a product of this solar maximum environment, and it won't be the last major active region we see before the cycle begins its eventual decline. Think about what this means for space weather threats. During solar minimum, you might go months without seeing a significant sunspot. X-class flares are rare. Major geomagnetic storms are unusual. Earth's technology operates in a relatively benign space environment. But during solar maximum, large sunspots appear regularly. X-class flares happen multiple times per month sometimes. Coronal mass ejections are common. The space environment around Earth is dramatically more hostile, more variable, more threatening to the satellites and power grids and communication systems we depend on. And here's the kicker. We're more dependent on space-vulnerable technology now than at any previous point in history. The last solar maximum, Cycle 24's peak around 2013 through 2015, was actually quite weak by historical standards. It was the smallest maximum in over a century. We didn't face many major threats during that period, which was fortunate because we were rapidly expanding our satellite infrastructure and becoming more technologically interconnected. But Cycle 25 is proving to be significantly stronger. We're facing a more active sun at a time when we're more vulnerable to its effects. This creates a challenging situation. On one hand, we have better monitoring capabilities than ever before. The satellites observing the sun, the models predicting space weather, the alert systems notifying stakeholders of threats. All of this infrastructure is more sophisticated than it was during previous solar maxima. We can see threats coming, we can prepare, we can take protective measures. That's genuine progress, real advancement in our ability to cope with space weather. But on the other hand, the systems we're trying to protect are more complex and more fragile than ever. Modern satellites are packed with sensitive electronics that can be damaged by radiation. Power grids are interconnected across vast distances, creating vulnerability to geomagnetically induced currents. GPS has become essential to countless applications that didn't exist during previous solar maxima. The internet connects everything in ways that create cascading failure risks. We've built a technological civilization that's exquisitely sensitive to space weather at precisely the time when we're facing one of the strongest solar maxima in recent memory. The December sunspot was a test of this dynamic. A major threat appeared, monitoring systems detected it, alerts were issued, stakeholders prepared, and ultimately we avoided the worst outcomes through a combination of luck and preparation. But it was just one test. There will be others. Throughout 2025 and into 2026, as we remain at solar maximum, more large sunspots will appear, more X-class flares will erupt, more CMEs will head into space, some of them aimed at Earth. The probability of facing a truly severe space weather event during this period is higher than it's been in over a decade. This isn't meant to be alarmist, it's meant to be realistic. Solar cycles are predictable in their overall pattern even if specific events remain uncertain. We know we're at solar maximum. We know this maximum is stronger than the last one. We know that stronger maxima produce more and larger solar events. Therefore, we can expect to face more significant space weather threats over the next couple of years than we've faced recently. That's just mathematical probability based on historical patterns. What can be done about this? At the individual level, not much, honestly. Space weather is not something personal preparation can address in the way you might prepare for hurricanes or earthquakes. You can't stockpile supplies that will protect your GPS receiver from a geomagnetic storm. You can't reinforce your home against coronal mass ejections. This is infrastructure-level risk, requiring infrastructure-level solutions. But at the societal level, there are measures that can and are being taken. Power grid operators have protocols for responding to geomagnetic storm alerts, including temporarily reducing power flow in vulnerable transmission lines, or taking transformers offline before they can be damaged. Satellite operators can reorient spacecraft to minimize radiation exposure during solar events, or put satellites into safe mode temporarily. Airlines can reroute polar flights during severe space weather to avoid radiation exposure and communication blackouts. These protective measures work, but they require advance warning, which is why the solar observation and space weather forecasting infrastructure is so critical. There's also ongoing research into better prediction methods, better understanding of solar physics, better models of how CMEs interact with Earth's magnetic field. Every solar cycle provides new data, new opportunities to refine our understanding. The December sunspot, despite not producing a catastrophic event, still provided valuable observations that contribute to this larger scientific effort. Every large active region, whether it erupts spectacularly or remains relatively quiet, teaches us something about how the sun works. For the interested public, the people watching this video, the most valuable thing you can take from the December sunspot story is awareness. Awareness that space weather is real. Awareness that the sun can affect Earth in practical, consequential ways. Awareness that we're living through a period of elevated solar activity and elevated risk. Not panic, not fear, but informed awareness that recognizes this aspect of our cosmic environment. If you're curious about staying informed on space weather, there are resources available. NOAA's Space Weather Prediction Center provides forecasts and alerts accessible to the general public. NASA's Solar Dynamics Observatory releases stunning images of the sun daily. Amateur astronomy communities track and discuss solar activity. You don't need a PhD in astrophysics to follow along with the basics of what the sun is doing and whether any active regions pose current threats. The information is out there for those who want to pay attention, and there's something empowering about understanding these threats rather than being blindsided by them. Previous generations had no warning when solar storms struck. The telegraph operators in 1859 had no idea what was happening when their equipment started sparking. They were victims of invisible forces they couldn't understand or prepare for. We're in a better position. We can see the threats. We can measure them. We can predict their arrival with reasonable accuracy. We can take protective measures. We're not helpless in the face of solar fury. We're not invulnerable, but we're not helpless either. The December sunspot reminded us of this balance. It showed us what a major threat looks like, what characteristics make a sunspot dangerous, what factors determine whether that danger manifests as catastrophe or merely as inconvenience. It was a classroom, in a sense, teaching lessons about space weather to those who were paying attention. And the fact that the worst didn't happen shouldn't make us dismiss those lessons. If anything, it should make us grateful for the opportunity to learn them without suffering the full consequences. As we continue through 2025 and approach 2026, the sun will keep doing what it does. New sunspots will appear. Some will be large, some will be complex, some will be both, like the December monster, and some of those sunspots will inevitably aim at Earth and erupt. It's not a matter of if, but when. The question is whether we'll be prepared, whether our monitoring systems will provide adequate warning, whether our protective measures will be sufficient, and whether we'll get lucky with the geometry and timing the way we did in December. Living at solar maximum means living with this elevated risk, this constant low-level concern that the sun might lash out and disrupt the technological systems we depend on. But it also means living in a time when we have the tools and knowledge to face that risk more effectively than any previous generation. We're not at the mercy of forces we don't understand. We understand solar physics better than ever. We observe the sun better than ever. We can protect ourselves better than ever. And that has to count for something as we navigate the peak of this solar cycle. One of the largest sunspots of 2025 targeted Earth and measured 10 times our planet's size. It was comparable in scale to the sunspot that caused the Carrington Event. It had the most dangerous magnetic configuration. It aimed at us during solar maximum, and we survived without catastrophic consequences. That's a win. But it's not the end of the story. It's just one chapter in the ongoing narrative of humanity living on a planet orbiting an active star, learning to cope with the reality that we're part of a dynamic solar system, whether we like it or not. If you found this story valuable, if understanding what happened in December and what it means for our near future matters to you, then subscribe to this channel, because space weather will continue to be relevant throughout this solar maximum and beyond. Hit that notification bell so you don't miss updates when significant solar events occur, and share this video with others who might benefit from understanding that the sun is not a static, unchanging ball of light in the sky, but a powerful, dynamic, occasionally threatening neighbour that we need to keep watching. We're all in this together, all of us living under the same star, all of us hoping that when the sun decides to show its power, we're ready to handle whatever comes our way.